Hello and welcome to another episode from Spiral Physics Education. To get the most out of this lesson, you need to know about the earth and neutral and live wires. You also need to know about the fuse and the earth wire and how they work together to keep us safe, and why fuses and switches must be attached in series with the live wire. And if you're unsure about any of those, check out the other video on the 3-pin plug on the channel. So let's start with calculating fuse sizes. So when we ever look at electrical devices, they've always got a bit of information on them that might look something like this. So this is some sort of large urn for hot water. And if we try to look at all of the information on there, we can see that we've got a voltage or a potential difference given as 230 volts. And we've also got something that tells us that it works on alternating current. And we've also got information there that tells us that what its power is, 1500 watts in this case. And we also get told about the frequency of the alternating current power supply. So lots of bits of information there on there, but really what we're going to be looking at is the power and the voltage to work out the current, because notice that there's no indication of what the current is. So let's have a look at it again. We've got the voltage at 230 volts, or the potential difference at 230 volts, and we've got power is 1500 watts from that information. So we're going to be using the equation power is current times voltage to work out the current. It's going to rearrange it. So current is power over voltage. And we're going to substitute in our values. Remember that power must be in watts and the potential difference must be in volts. And that tells us that when it's working normally, this urn has a current of 6.52 amps flowing through it to two significant figures. So the question now is, which fuse should we fit into this urn's plug? So I'm going to give you the option, a 3 amp, a 5 amp or a 13 amp fuse. Well, a 3 amp would be too small, a 5 amp would be too small, so we've got to have a 13 amp fuse. If we placed a 3 amp or a 5 amp fuse into this device, the wire inside the fuse would heat up and it would melt and it would break the circuit straight away, so it would never work even when it would be okay and safe to work. Okay, so let's have a look at another one. So this is a pedestal fan. Lots of information on there again, but from that we can see that the voltage is 230 volts again, and that the power this time is 120 watts. So we're going to use this equation again, going to rearrange it, plug in our power and potential difference, and we get this time a current of 0.52 amps. And we're going to select a fuse from 3, 5 or 13 amps. So we always choose the next fuse up, and the next fuse up from 0.52 amps is 3 amps. A 5 amp fuse and a 13 amp fuse would work fine with this. So it's not that it would stop this device from working, but it works correctly when 0.52 amps is flowing through it. Now, if 5 amps were to flow through it, 10 amps were to flow through it, that might start damaging components in the fan. Plastic in the fan might start melting, and it could start a fire. So we certainly don't want the current to go up too high beyond the fuse rating. So that's why it's important to select the next fuse up. We don't want to put too high a fuse in there because that could lead to electrical fires. Let's have a look at another one. So lots of information on this fridge here. And if we look on the right hand side, a little bit blurry maybe, but up there it says that the voltage or the potential difference is 230 volts. It says on the left hand side there that the related power input is 100 watts. Let's leave it at that. And therefore we can use this power is current times voltage. Now rearrange it. Power is 100 divided by 230 volts for our potential difference, and that means that this fridge is delivering, or having delivered to it, 0.43 amps. And again, select from 3, 5 or 13 amps. The next one up is a 3 amp. And once again, it would work fine with a 5 or a 13 amp fuse, but it's best to select the next one up because too high a fuse fitted could mean that the current could go up much higher than the 0.43 amps and melt components and cause electrical fires. So circuit breakers, well, circuit breakers often look like this. So this is a home consumer unit that's got lots of different circuit breakers in there, and there'll be a consumer unit like this somewhere in your home. And if you look in labs, each individual lab usually has its own consumer unit to protect the people in it, and they're near the electricity meter in your home. And what we have here are an array of circuit breakers. Each one of those is a switch that looks like this. So that's a circuit breaker that's been removed from the consumer unit, and it behaves a little bit like a fuse. And what we can say here is that the circuit breakers behave like an electrical fuse. So what happens is if the current flowing through the circuit breaker gets to a point where it's too large, then it turns the switch off, and the switch can be easily reset. So rather than anything like a wire permanently breaking, an electrical switch is flicked when the current gets too large, and therefore it can be easily reset. And if you look carefully on that image on the bottom, you can see where it says you've got an on-off switch there to helpfully reset it. And that's one of the advantages of a circuit breaker, is that they can be reset very easily where fuses must be replaced. So let's have a look at how a circuit breaker actually works. So in this diagram here, if I talk you through it first, we've got from the top left hand corner where it says on, we've got a power supply, and the current is going to go up, and it goes through an electromagnet. So the current going through the electromagnet is going to magnetize the electromagnet, and then the current goes down, and then it flows through something that looks like a push switch is on to the rest of the circuit, and then it comes back. So when it's working normally, the electromagnet is magnetized, but there's only a relatively small current going through the electromagnet, so the electromagnet isn't actually strong enough to pull out the iron bolt that holds the plunger in place. So if we have a look at where it says iron bolt holds plunger in place, there's a spring attached to it, and what that electromagnet is going to do, it's trying to draw that iron bolt towards it, but there's a spring pushing back against it. And what that iron bolt is doing is it's holding in place a plunger that is plastic, and that's that vertical plunger. So it's working normally at the moment, and like I said, the current isn't large enough to pull out that iron bolt. So this is where the current's going. And everything is working fine at the moment, so there's no problems. So we're going to introduce a fault to it, and the fault that occurs is actually going to cause the current to flow, to be larger, and that's really important. So when the current flow is much larger, the situation for this circuit now changes. The current increases, so the electromagnet increases, and that allows the iron bolt, to be attracted towards it, which pulls the iron bolt out of a recess of the plastic plunger, and then that plastic plunger is forced upwards. Notice then the switch down at the bottom is now off, and that's really important, so that that breaks the circuit. And if you look at the top, it says a reset button. To reset it, all you need to do is push that down so that the iron bolt is able to fit back into the recess of the iron bolt. So this is a residual current device, RCD device, and these are usually attached to gardening equipment that you plug in, so like lawn mowers and hedge trimmers and things like that. And what they do is that they monitor the current going along the live wire, and they're constantly comparing it to the current flowing back along the neutral wire. And if the current flowing back along the neutral wire is less than the live wire, it stops the current flowing. And what it's assuming is that some current flowing from the live wire is going somewhere else, and it could be going through a person, so it cuts off the electricity supply. And it can be reset easily. In this case, there's an orange button that can just be pressed to do that. So let's look at how something like this might work. So here we've got our residual current device, and we've got this time 2 electromagnets. And what we're going to do is just follow the path of the current along the live wire through the first electromagnet to the electrical device and down by the neutral wire. Now what that means is the current, when it's working normally, is going to be the same in both the live wire and the neutral wire. So the strength of the electromagnets in both of those are going to be identical. So just above it there is a pivot with a device which is made out of iron, and that iron horizontal rocker, if you like, is going to be pulled down equally to both the neutral wire and the live wire. If you like, the moment produced by both of those electromagnets is going to be identical. So that force down there is going to equal to that force down there. It's going to be completely balanced because the moments are going to be equal. Now let's suppose that the current flowing along the live wire is larger than the current flowing along the neutral wire. And that means that some of the current at the electrical device is seeping off, and it might be going through a person down to the earth. They're getting slightly electrocuted at this point. Now that means that the current flowing along the live wire is larger, so that live wire electromagnet is stronger, and that means that the neutral wire is going to magnetize the other electromagnet, but not by as much, so that force is going to be a little bit weaker. And that means that the pivot is going to tilt. And if you look at the top, that's broken the circuit, so there's no more current flowing through it, so it's broken the circuit. And all you need to do is press down that switch at the top to reset it. So that's how a residual current device works. It just compares the current flowing through the live wire to the neutral wire, and if the neutral wire current is smaller, it breaks the circuit. So let's look at how fuses compare to circuit breakers and residual current devices. So with a fuse, remember that it's a wire in the fuse and it heats up, and that's going to melt and it's going to break the circuit if too much current flows. With a circuit breaker, when the current increases, here we have an electromagnet become strong enough to pull a component out of position, which breaks the circuit. And with a residual current device, it compares the current flowing through the live wire and the neutral wire. And if the live wire current is larger, then it breaks the circuit and stops the current flowing through it. The thing is with the fuse though, once the fuse is broken, it can't be reused and it must be replaced. With a circuit breaker, it's really easy to reset. So a reset button allows the circuit breaker to be reused indefinitely. So it's reused or reusable. And very similarly for a residual current device, exactly the same thing. It can be reset indefinitely. It doesn't matter how many times that it's set or reset. With a fuse, they're actually very slow to react to increases in current. So it might be that you might have a 5 amp fuse, but the current might go a bit above 5 amps before it's actually heated up enough to melt and break the circuit. So they do require some time to react to fast changes in current. And as we said, they're not reusable. But they are cheap, which is a positive. Circuit breakers, they're expensive. They're difficult to produce, unlike just a wire for a fuse, but they're quick to react to changes in current. They are reusable and they're very reliable. Residual current devices, well, again, they're expensive. They're also quick to react, they're reusable, they're reliable, and they're sensitive. So they're the ones that compare the current flowing from the neutral wire to the live wire. It doesn't necessarily need the live wire current to go up. It compares the current in two wires, and if they're not identical, then they get cut off. So I hope that you found this episode on fuses, circuit breakers and residual current devices useful. Don't forget to subscribe to the channel and check out other videos on the topic and other topics. And I'll see you next time on Spiral Physics Education. Goodbye. In this episode,